So let us today start with the second exercise because we did the first one in the last video. So in this second one, we have this relation on the set of all real numbers. What does this relation do? It relates the real numbers a and b. That is, under this relation, a is related to b if a is less than or equal to the square of b. We have to show that it's neither reflexive nor symmetric nor transitive. So let's see the solution. Okay, so this is the solution. In the solution, we first of course show that R is not reflexive. Note that the square of 1 divided by 2, which is 1 over 4, is less than 1 divided by 2. This means that 1 over 2 comma 1 over 2 is not in R. For this element, for this ordered pair to be in R, this square should be greater than or equal to 1 over 2 according to the definition of R, but that's not the case. So this element does not belong to R, and that makes R not reflexive. Next we go for symmetry. 1 is less than or equal to 2 square. In fact, 1 is strictly less than 2 square, but of course 2 is not less than or equal to 1 square. So this inequality tells us that 1 comma 2 belongs to R, and this one tells us that 2 comma 1 is not in R, and that's why R is not symmetric. Finally, we go for transitivity. 1 is less than or equal to minus 3 square because this will be 9, and similarly minus 3 is less than or equal to 0 square because minus 3 is negative. But 1 is not less than or equal to 0 square. So this inequality and this inequality, they give us respectively the fact that 1 comma minus 3 and minus 3 comma 0 are both elements in R. That is, 1 is related to minus 3 and minus 3 is related to 0. But because you do not have this inequality, so 1 comma 0 is not in R. So R fails to be transitive. So that's the solution. Next we have 3. So here the set on which we are going to have a relation is the set of the first 6 positive integers, and this is the relation. Any two elements a and b from this set are related to each other in that order, that is, a is related to b if b is 1 more than a. We have to see if this relation is reflexive, symmetric or transitive. So let's see the solution. Okay, so this is the solution. This one is the same as the last one. Same means similar. Okay, it's neither reflexive nor symmetric nor transitive. First we note that 1 comma 1 is not in R because 1 is not 1 more than 1. They are the same in fact. So R fails to be reflexive. Next, 1 comma 2 belongs to R because 2 is 1 more than 1, but 2 comma 1 of course is not in R, so R is not symmetric. Finally, 1 comma 2 and 2 comma 3 both belong to R because 2 is 1 more than 1 and 3 is 1 more than 2. But 1 comma 3 is not in R because 3 is 2 more than 1, not 1 more than 1, and that makes R not transitive. Let us see the next one. The solution. This solution is pretty easy. There is almost nothing to do here. Everything follows from properties of real numbers. First we see reflexivity. So we take any real number a. Obviously a is less than or equal to a. That means a comma a by the definition of R is an element of R. And this is happening for every a in R, and that is why R is reflexive. Next we go for transitivity because that is being claimed that it is transitive. So we take 3 elements in R, not necessarily distinct. 2 of them may be the same, or in fact all of them may also be the same. But anyway, such that a comma b and b comma c both belong to R. So by the definition that means a is less than or equal to b and b is less than or equal to c. But then we know that in such a condition a is less than or equal to c. So A comma C belongs to R, and that is why R is transitive. But R is not symmetric, that also we have to show, which easily follows from this. 1 comma 2 is in R because 1 is less than or equal to 2, but 2 is not less than or equal to 1. So 2 comma 1 is not in R. So R fails to be symmetric. So that's the solution. Next. So this fifth one also involves this less than or equal to, but it's slightly different. It's not ordinary less than or equal to relation. This relation is also on the set of all real numbers, and it relates the real number a to b if a is less than or equal to the cube of b, b cube. And we have to see whether it's reflexive, symmetric or transitive. So let's see. So here's the solution. Again we consider this 1 over 2 comma 1 over 2. The cube of 1 over 2 is 1 over 8, 1 divided by 8, and that is less than 1 divided by 2, not greater than or equal to 1 divided by 2. That is why this ordered pair is not in R. So that's why R is not reflexive. Next, we note this. 1 is less than or equal to 2 cube because 2 cube is 8, but 2 cube is not less than or equal to 1. So 1 comma 2 is in R, but 2 comma 1 is not in R. So R is not symmetric. And finally, you can guess that it will also not be transitive. That is the case. 27 is less than or equal to 3 cube. Actually, they are equal. Similarly, 3 is less than or equal to cube of the cube root of 3. So here also they are equal. And these two inequalities tell us that 27 comma 3 as well as 3 comma cube root of 3 both belong to R. However, 27 is not less than or equal to this cube of cube root of 3 because this side is 27 and this side is 3. So this ordered pair is not in R. So that makes R not transitive. So it's like those two relations, neither reflexive nor symmetric nor transitive. Next. In this next one, the sixth one, the set is quite small. It has only these 3 natural numbers. And the relation also is very small. It has only these 2 ordered pairs, 1 comma 2 and 2 comma 1. We have to show that this relation is only symmetric. It is neither reflexive nor transitive. And the solution is also quite straightforward. Because we have both 1 comma 2 and 2 comma 1 in R, R is symmetric. Nothing else is there. So say if you had, it's not there in R, but if you had 1 comma 3 for example, but not 3 comma 1, then R would not have been symmetric. But such elements are not present. So that makes R symmetric. R is not reflexive, that's quite easy to see. For example, 3 comma 3 is not in R. Actually, none of this type of elements is in R. R has neither 3 comma 3 nor 1 comma 1 nor 2 comma 2. But absence of any one such element makes R not reflexive. Next we go for transitivity. We have 1 comma 2 and 2 comma 1 in R, but 1 comma 1 is not in R. So R is not transitive. Next. In this 7th one, you won't really see exactly these wordings. I have changed the wordings slightly to make it more comprehensible. Let A be the set of all books in some library of a college. And on A, we have this relation, which of course would relate 2 books from that library. And the ordered pair of books is X comma Y. So here X and Y are 2 books from that library. We say that X is related to Y if X and Y have the same number of pages. We have to show that this is an equivalence relation on A. It is almost just an exercise of simply writing some sentences. You practically don't have to do any kind of mathematics. How do you show that this is an equivalence relation? So you need to show 3 things. It should be reflexive, symmetric and transitive. What do we need for reflexivity? You take any book from that library, X. X and X have the same number of pages. because we are talking about only one book. So that makes x comma x an element of R, so R is reflexive. So you write that. Next you take two books x and y such that x and y have the same number of pages. Then y and x also have the same number of pages. So y comma x will also belong to R. So that way R becomes symmetric as well. And by now you can see very easily why R would be transitive as well. You take three books, not necessarily distinct, x, y and z from that library, and say x is related to y and y is related to z. That means x and y have the same number of pages and y and z have the same number of pages as well. So obviously x and z also should have the same number of pages. So x comma z will also be in R. So that makes R transitive. So that is why it's an equivalence relation. You just have to write these things. There is no mathematical twist, nothing is there. You don't even have to find those elements that we had to find in the other solutions, say 1 divided by 2, cube root of 3, nothing like that is present here. So I leave the writing of the solution to you. Okay, and let's move on to the next one. In this 8th one, which will be our last problem for today in this video, it seems big because there is something extra to be done besides showing that this is an equivalence relation. So the set on which the relation is defined is this set, consisting of the first 5 positive integers, natural numbers. And this is the relation R. It relates two elements A and B of this set if the absolute value of the difference between A and B is an even integer. And we have to prove first that this is an equivalence relation. That is the first task. The second task is we have to show that all the elements of this set 1, 3 and 5 are related to one another. And the third thing is that we have to show that both the elements of this set are also related to each other. And finally there is one more thing to show. No element of this set is related to any element of this set. Okay, so let's see the solution. Okay, so the solution starts usually by considering any element of A. So you may see that for the first part of the solution, we don't really have to bother about what the elements of A are, although we know that they are the first 5 positive integers. So we take any element A in A. Now if you calculate this difference, it is 0 and 0 is an even integer. So by the definition of our relation, A comma A will belong to R, regardless of what A actually is. And that makes our relation reflexive. Next we go for symmetry. So we take any ordered pair A comma B in R. This means that A and B are two elements in A such that this numerical difference between A and B is an even integer. But then this is also an even integer, and actually this is nothing but that difference itself, because we have modulus. So whether you consider A minus B or B minus A, the modulus is going to be the same. It's like considering the modulus of 3 and the modulus of minus 3. Both are equal to 3, like that. So that way B comma A also belongs to R, and so R is symmetric. And finally we need transitivity. So we take these two ordered pairs in R, A comma B and B comma C. This means that A, B and C are 3 elements in A such that this difference mod A minus B and this difference mod B minus C are both even integers. And now we need to show that the difference mod A minus C is also an even integer. However, immediately you get stuck a little. So far things have been going smoothly, but now what will you do? How do you get mod A minus C from these two things? Let's see. Let us consider a minus c first, okay, without modulus, just ordinary a minus c. A minus c of course is equal to a minus b plus b minus c. Now depending on which one of a or b is greater and which one is smaller, this a minus b is either mod a minus b itself or minus mod a minus b. If a is greater than or equal to b, then this mod a minus b with a plus sign is equal to a minus b. In other words, looking from the other direction, if a is greater than or equal to b, then a minus b is equal to mod a minus b. Otherwise, if a is less than b, if you come straight from here to here, it may be a little confusing. You think of the module in terms of modulus first. Now we consider the second case. A is less than b. Then forget the sign for a moment. Just plain mod a minus b. What will that be? That will be equal to b minus a. Why? Because a is less than b. So a minus b is negative. So its modulus will be minus of a minus b, that is b minus a. But we do not have b minus a here. We have a minus b. So if mod a minus b is equal to b minus a, that means minus mod a minus b will be equal to a minus b. So we see that depending on which one is greater, which one is smaller, this is equal to either mod a minus b or minus mod a minus b. That's why we can write plus or minus. Similarly, in place of b minus c, we can write this, plus or minus mod b minus c. So this is one thing. And similarly, if we consider c minus a can be written as c minus b plus b minus a. Now by a similar argument, c minus b is equal to plus or minus mod c minus b actually. But mod c minus b is equal to mod b minus c because inside modulus you can change sign. Just like that, b minus a is plus or minus mod b minus a, but that is also plus or minus mod a minus b. So we see that both a minus c as well as c minus a are equal to plus or minus mod a minus b plus or minus mod b minus c. Plus or minus mod a minus b plus or minus mod b minus c. Now we come to the absolute value of a minus c, mod a minus c. Because mod a minus c is either a minus c or c minus a, and both of them are equal to this same thing, so mod is equal to this thing. Okay. Now you can see that you can use this information here. This is even, okay, mod a minus b is even, forget about the sign, mod b minus c is also even. So even if we have a negative sign in front of an even integer, that will also be even. So after all, we are adding two even integers, regardless of their sign. There may be positive, negative, anything can happen, but both of them are even. And that is why this sum would be even, and that way mod a minus c would be even. So here we write the conclusion. So because of this thing and the fact that these two are even, this is also an even integer. So that makes this ordered pair a comma c an element of R, and that is why R is transitive. So being reflexive, symmetric and transitive, R is an equivalence relation. Now we go to the other parts. So in the other parts, first we consider this set consisting of 1, 3 and 5. Note that these are precisely the odd integers in our original set A. So if we now choose any two elements A and B from this set, note one more thing carefully, that this A and B are not necessarily distinct, they may be equal also. But regardless of what the situation is, A and B are both odd integers. So this difference is even when you take the difference of two odd integers, it is an even integer, and the absolute value of that, modulus of that, is also an even integer, non-negative even integer. But then by definition a comma b belongs to R, so that way any two elements of this set are related to each other. And similarly, in both of these elements of this set are related to each other. Yeah, the thing is same, I mean the pattern is same, but there is a slight difference. Now our A and B are both even. So for them also this will be even. So here also A comma B belongs to R. And finally comes the last part, where we have to take one element from here and one element from there, and they will not be related. So accordingly, in this final part, we take one element from this set, let us call it A, and one element B from this set. Then A is odd and B is even, but then their difference is odd, it's not even. And the absolute value of that is also an odd integer, a positive odd integer. But that makes this ordered pair not an element of the relation R. Okay, so that's what we had to show. So let's end the video here itself, and tomorrow I think we have commutative algebra. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.